Very good evening to one and all present in this webinar. I am Esakkirajan, working as professor in the Department of Instrumentation and Control Engineering, PhD College of Technology, Coimbatore. The topics of presentation for this webinar are the following. First, the signals, the definition of the signal, different types of signal, and various mathematical operations that are performed on the signal. Then system, the meaning of the system, how we can classify system into different categories, and then properties of the system. The next topic would be transform, its need, types, and then application, followed by filters. Three different types of filters what we will be covering in this webinar would be recursive filter, non-recursive filter, and then adaptive filter. First, we will start with the definition of the term signal. Signal is basically a physical quantity which varies with respect to time or space. In general, it is a function of one or more independent variables. It can be considered as a record of physical activity. Most of the real world signals are analog in nature. Now, what are all the different types of analog signals that we are experiencing in our day-to-day life? It is summarized in this slide. So we have temperature, pressure, and then level, followed by voltage, current, power. Other than this, we have acceleration and then torque. So all these signals are mostly analog in nature. Now, what are all the signals that are there in the human body? For example, if we take brain, the electrical activity of the brain, we used to call it as EEG signal. It plays a very important role in sleep pattern analysis, detection of seizure, detection of epilepsy, and so on. Then electrical activity of brain, we have EEG. Like that, we have electrical activity of the heart. We call it as ECG signal. And then we have PCG. PCG stands for phonocardiogram signal, which is called as heart sound, lup dub sound. So here we are coining it as S1 and S2 sound. Like that, we have EOG signal, EOG electroocularogram signal. It is mainly useful for the detection of drowsiness. Then we have EMG electromyogram signal, which is basically electrical activity of the muscle, which is used to find out muscle fatigueness. Other than this, what how we can classify signals? So these are all different types of signals. Based on what factor we can classify signal into different groups. One of the factor is dimension, the other one is nature of the signal. So here dimension refers to number of independent variables that are required to represent the signal. Based on dimension, the signal can be classified as one dimensional signal, two dimensional signal, and multidimensional signal. Based upon nature, we can classify the signal into deterministic or random. So if we know the nature of the signal without any ambiguity or uncertainty, then we can represent the signal in terms of mathematical expression, then it becomes a deterministic signal. If we don't have a thorough knowledge about the signal, we call it as random. Second classification would be whether the signal is going to take continuous or discrete value. We have continuous time signal, discrete time signal, digital signal. If the signal is going to repeat itself in an identical way, then it is a periodic signal, otherwise it is aperiodic. If the signal is having a finite energy, then it is an energy signal. If it is not having finite energy, if it is having a finite power, then it becomes power signal. If the statistics of the signal do not change with respect to time, then it becomes stationary signal, otherwise it is non-stationary. Next, example of one-dimensional signal, what is being given in this slide. On the left-hand side, you have ECG signal. On the right-hand side, you have EEG signal. Example of two-dimensional signal, we have image. One is the famous person Einstein, and the other one is Mother Teresa. Here, there is a variation in the intensity along x and y direction. That is the reason why it is called as two-dimensional signal. How we can represent signal in different forms? So, one is graphical form, the next one is functional form, then tabular form, and then sequential form. So these are all the ways by which we can represent the signal. Standard test signals, for example, you have unit sample sequence, unit step signal, unit ramp signal, and then exponential signal. How to represent these standard signals in four different forms of representation is illustrated here. For example, unit sample signal, what is the graphical representation, and what is the functional representation, and tabular followed by sequential representation. That is, unit sample sequence is going to take a value of 1 at n equal to 0, and the value is 0 otherwise. This unit sample sequence can be used to express any arbitrary sequence. That means any arbitrary sequence can be expressed in terms of weighted shifted unit sample sequence. That is the significance of the unit sample sequence. Next sequence what we have is unit step signal. So unit step signal, actually it represents the sudden change. So whenever we have a sudden change, that can be represented by means of a unit step signal. Four different forms of representation of unit step signal is given here. If we want to represent a gradual variation, then it can be done by means of unit ramp sequence. So the graphical form, the functional form, the tabular form, and the sequential form of unit ramp sequence is shown here. So it represents a gradual change. Then comes the exponential sequence. This we can broadly classify into two categories. One is real exponential, the other one is complex exponential. For example, if we take a complex exponential sequence, it is represented by e power j omega n. So x of n equal to e power j omega n if we assume the amplitude to be equal to 1. So in that case, how to represent this angular frequency omega? So angular frequency omega in degrees is represented like this. So 0 degree, 90 degree, 180 degree, and so on. In terms of radians, it is represented as 0, pi by 2, pi, 3 pi by 2, and then again 2 pi. So from this, what we can understand is this frequency omega is unique in the range 0 to 2 pi, or from minus pi to plus pi. So what will happen if omega is equal to 0? If omega equal to 0, then we have x of n equal to e power 0 n. E power 0 is 1. That means we will be able to get a constant signal of amplitude 1, that we call it as the DC signal. So it doesn't represent any variation. So DC signal don't have any frequency. So it is basically a DC signal. Here, if omega equal to pi by 2, we will be able to get the signal like this. On the other hand, if omega equal to pi, we will be able to get the signal like this. So it is oscillating between plus 1 and minus 1. In other words, it is toggling between 1 and minus 1. It is the highest frequency digital signal. Then omega equal to 3 pi by 2, we have a signal like this. And for omega equal to 2 pi, again we will have the DC signal. That means when omega, that is the angular frequency, digital frequency omega, is unique in the range 0 to 2 pi, or from minus pi to plus pi. Now comes the next topic, signal processing. So just now we have discussed about signal. So what is meaning of signal processing? So it is basically generation, transformation, extraction, and interpretation of information from the signal. We used to call it as signal processing. So how we can classify signal processing, and what are all its implications, that we will try to discuss in this. So signal processing, so what is the meaning, and what are all the different types and classic examples? So meaning, as we have discussed, it is basically extraction of information from the signal that can be done either in the time domain, or it can be done in the frequency domain. Two broad categories of signal processing are analog signal processing and digital signal processing, ASP and DSP. Classic examples include filtering, tracking, and then reduction. Now, we will see a simple example of how analog signal processing is different from digital signal processing. Analog signal processing, it will suffer from both long-term drift as well as short-term drift, but it will be minimal in the case of digital signal processing. The flexibility is less in the case of ASP, whereas DSP is more flexible. The reproducibility is less, and DSP is more reliable because of less number of components. So in that way, digital signal processing is better than that of the analog signal processing in many scenarios. The general flow of subject will be like this. So first we will have signals and system, then we have DSP, then we have advanced digital signal processing. In DSP, the main focus will be on three important aspects. One is generation of signal, analysis of signal, and then processing of signal. During generation, we will talk about continuous, discrete time, and digital. Naturally, there will be discussion on sampling, sampling theorem, violation of sampling theorem. We used to call it as aliasing. Analysis refers to extraction of useful information from the signal. Transform plays a very big role in the analysis of the signal. Different types of transforms like Z transform, Fourier transform will be discussed. Processing refers to manipulation of the signal. It can be done by means of filters. Two prominent examples of filters are non-recursive and recursive filter, are FIR and IR filter. In ADSP, how to move from single rate system to multi-rate system, and how to design a filter whose characteristics we can change with respect to external environment. We have adaptive signal processing. The backbone to adaptive signal processing is statistical signal processing or optimal filter. Then how to extend all this idea to multi-dimensional signal processing. So here image processing, video processing comes under the category of multi-dimensional signal processing. This gives the general overflow of the subject. So the idea of signal processing, general idea is explained in this slide. That is, most of the real world signals are analog in nature. If we want to process that signal by means of a computer or a hardware, we want to convert that signal from analog to digital. And then after processing, we are supposed to get back to the analog world or the real world. So the term processing refers to filtering. It can also represent detection. It can also represent coding. It can also represent synthesis, recognition, prediction. So these are all different terminologies that are used to represent the term processing. So let us take a very simple example of filtering. So this is a very famous scientist. Unfortunately, the image is corrupted by means of a noise. So if we perform filtering over this image, we will be able to get a good quality image. So filtering refers to removal of unwanted information from the signal. Another classic example of processing is detection of faults in power line. So our power line may suffer from spike. Here the example shown here is spike, then sag. It can also suffer from swell, then momentary interruption. So this refers to momentary interruption, harmonics or DC offset. So how to detect all these types of faults in the power line and how to overcome this faults, signal processing plays a very important role in this. Now the impact of DSP in day-to-day life, it is given here. In the cellular or mobile telephone, we have voice, speech processing plays a very important role. Then in the case of digital audio, we have audio equalization. It plays a very important role in the case of automotive electronics. So how to design an active suspension, and in the case of medical electronics, how to extract useful information from both one dimensional as well as multidimensional signal which are of biomedical in nature. It can be ECG, EEG, X-ray, CT, and so on. Then we have personal computer, sound cards, we have multimedia, modems. In all these things, DSP plays a very, very important role. The next topic what we want to highlight is basically this system. So coming from signal to system. So what is basically a system? System, it can be considered as an operator which operates on the input signal in order to get an output signal. It is normally represented by y of n is equal to transformation of the signal x of n. X of n is the input signal and y of n is the output signal. Now, the input to the system, it is also termed as excitation. The output of the system is termed as the response of the system. The general view of the system is given like this. System, basically it is used to perform meaningful operation on the signal. The input to the system, we call it as the excitation, and the output of the system, we call it as the response. The system is characterized by its impulse response. So x of n is the input, y of n is the output, h of n represents the impulse response of the system. If the system is linear and time invariant, we have the freedom to express the output as y of n is equal to x of n in convolution with h of n. This is true if the system happens to be LTI. This is the general holistic view. This system can be an amplifier, it can be an oscillator, it can be a rectifier or a filter. Now, the response, how the system is going to respond to the input, we call it as the response. So this response we can classify into three broad categories. If the system, how the system is going to react to the input, that is unit sample signal, we call it as the impulse response of the system. So impulse response refers to how the system is going to react to del of n, we call it as the impulse response. How the system is going to react to unit step signal, we call it as the step response. And how the system is going to react to complex exponential signal, we call it as the frequency response. In general, this frequency response is a combination of magnitude response and phase response. Now, what are all the ways by which we can describe the system? So, one classic way is to represent in terms of difference equation. If the system happens to be discrete, then we can relate the input and the output of the system through linear constant coefficient difference equation, which is represented like this. Then the next way is by means of the transfer function. Then we have pole zero diagram. Then we have frequency response. Along with that, we have block diagram approach and so on. LCCD, linear constant coefficient difference equation, it is represented like this. So this equation represents that weighted combination of output will be equal to weighted combination of the input. Transfer function, a numerator polynomial in Z divided by the denominator polynomial. Numerator polynomial corresponds to zeros, whereas the denominator polynomial corresponds to poles. The pole zero diagram is represented by this diagram. So we all know that we can very easily find whether the system is stable or not. If the pole lies within the unit circle, then the discrete time system is stable, otherwise it is unstable. In general, the frequency response is a combination of the magnitude response and the phase response. So these are all the different responses of the system. Now comes the next question, how to classify the system? On what basis we can classify this system? So three different bases are given here. One is based on the nature of the input output signal. Another one is based on number of input and output signal. And the third one is with respect to the property that the system is going to satisfy. Based on the nature of input output, it can be classified as continuous time system or discrete time system. Based on number of input output, it can be single input, single output, SIMO, MISO, or multiple input, multiple output system. Based on the property, it can be a linear or a non-linear system. If a system is obeying superposition principle, that is homogeneity and additivity property, it is a linear system, otherwise it is non-linear. Time shift in the input, if it results in time shift in the output, then definitely it is time invariant system. If the system is non-anticipatory, then it is a causal system. If bounded input results in bounded output, then it is a stable system. If the system don't have memory, that means the current output depends only on current input, then it is a static system. If the system is having memory, then it means that output of the system depends on either the past input or the past output, then it becomes a dynamic system. If distinct input results in distinct output, then it is invertible system, otherwise it is non-invertible. So these are all the various classification of the system. So what is basically an LTI system? So we know very well that LTI systems are completely characterized by its impulse response. So if we know the impulse response of the system, we can say whether the system is causal or not. So h of n is equal to 0 for all n less than 0, it is a causal system. This is the condition for memoryless system, and if the impulse response is absolutely summable, then it is a stable system. Then if the impulse response satisfies this condition, then it is a invertible system. That means the impulse response completely characterizes the LTI system. This is what we want to highlight. Then the next topic what we want to give an overview is transform. So transform is basically a representation of the signal. The signal is represented in terms of the basis function. Different basis function naturally gives rise to different transform. So the need of the transform is explained by means of a simple illustration. Here we have a white light which falls on the prism, and we are able to get VGR at the other end of the prism. This phenomenon we used to call it as dispersion. That is splitting up of white light into its constituent colors, we call it as dispersion. If a person is here on the left hand side of the prism, he will be able to see it as a white light. If a person is on the other end of the prism, he will be able to see the white light as a combination of 7 colors. That means person on the right side of the prism, he is getting maximum information than the person who is on the left side of the prism. That means prism is able to give some insight about the white light. That is, white light is a combination of 7 color. Similar to that of the prism, we have transform. Transform allows us to know what are the frequencies that are available in the given signal. So this transform, we can use it to analyze both signals as well as the system. So that is being illustrated here. What are all the transforms that are exclusively used for signal study, and what are all the transforms that are exclusively used for system study? If my signal happens to be continuous time Fourier transform. If it is discrete, DFT. Then to analyze continuous time system, Laplace transform is exclusively used, and to analyze discrete time system, we have Z transform. One of the important characteristics, it allows us to move from one domain to another domain. The forward transform is always known as the analysis, and the inverse transform is known as synthesis. Now, one of the prominent transform is basically Fourier transform. It was put forward by John Baptist Joseph Fourier in the year 1809. So while he was studying the flow of heat through the object, he was able to develop the transform. The 4 different flavors of Fourier transform are continuous time Fourier transform, discrete time Fourier transform, discrete Fourier transform, and computationally efficient form of DFT, we call it as fast Fourier transform. So this is being given here. The relationship between this is given here. So if my signal is continuous, we can analyze using continuous time Fourier transform. If we sample the signal, we are moving from continuous time Fourier transform to discrete time Fourier transform. If we sample the spectrum, we will be moving from DTFT to DFT. Computationally efficient form of DFT, we used to call it as fast Fourier transform. So DFT, the idea is explained here. We have x of k, which represents the spectrum, which is basically obtained by taking n point DFT of the signal x of n. So here x of n represents the signal e power minus j 2 pi by n kn, which is basically a complex exponential which represents the basis function, and x of k represents the spectrum. Now we are going to take a specific value. For example, if n is equal to 4, naturally k will take the value from 0 to 3. So for k equal to 0, what is the expression? Capital X0. For k equal to 1, k equal to 2, and k equal to 3. if we are able to collect the coefficient, we will be able to get the DFT matrix in this way. So DFT matrix, it is basically a symmetric matrix which can be used to compute the spectrum of the signal. So this 4-point DFT of the signal x of n is equal to 1111. How to obtain is given in this slide. So if my signal happens to be 1111, the significance is there is no variation in the signal at all. It is a DC signal. If we take 4-point DFT of the signal, we are able to get the spectrum as 4 followed by 3 zeros. Now, this is the signal and this is the corresponding spectrum. So what we can observe is the signal is a DC signal. We are able to get the coefficient k equal to 0. The value is equal to 4. Remaining all the coefficients are 0. Now comes the next interesting aspect. We are going to multiply the previous signal x of n by a complex exponential, that is e power j pi n. That means all 1 turns out to be 1 minus 1, 1 minus 1. That is, the signal x of n is multiplied by means of a complex exponential in order to get the signal 1 minus 1, 1 minus 1. So here it is basically a AC signal. If we take DFT of this signal, we are able to get the spectrum as 0040. Now you can see that this is the signal and this is the corresponding magnitude spectrum. Now we will try to compare these two examples in a single slide. That means if the signal happens to be a DC signal, we will be able to get the coefficient at k equal to 0. Here the signal x of n is multiplied by a complex exponential. Always it results in the frequency shift. So multiplying a signal by a complex exponential results in a frequency shift. This is what we are able to explore. The main drawback of DFT is it is computationally intensive. That means n-point DFT requires n square complex multiplication and n into n minus 1 complex additions. In order to overcome this computational complexity, people developed fast Fourier transform. Here, this fast Fourier transform is based on divide and conquer approach. It makes use of the symmetric as well as the periodicity property of the complex exponential. So this FFT we can broadly classify into different categories like decimation in time, decimation in frequency, and then we have radix 2, radix 4, and then split radix algorithm. For an illustration, we have given the decimation in time fast Fourier transform algorithm for a 8-point DFT. So here the input signal are all ones. So in the DFT, that is, we are computing the DFT through decimation in time algorithm. That means we will have 3 stages in the butterfly diagram, that is S1, S2 and S3, and these are all the butterflies in the first stage, second stage, and then in the third stage, and the corresponding Tudor factors. The input will be in bit reversal order and the output will be in the natural order. So bit reversal order x0, 4, 2, 6 even samples followed by the odd samples, that is being illustrated here. Now we are going to pump in the signal. The signal value are all ones. So here we are going to feed the input to this butterfly and then we want to see the output. Now you can see that this 1 and 1 are going here and then we are able to get the output. So how it is being traversed through this butterfly diagram is illustrated by this simple animation. So the input is progressing and then we are able to get the output in this way. See here 2 is coming here. So 2 plus 2 it will be 4. Remaining values will be simply 0. Now from the second stage, the value will be going to the third stage. So 4 will be moving here in order to get the output as 8 followed by 70. So the idea here is if your input is a DC signal, then your output is basically the first coefficient will have the sum of all the values, remaining all the coefficient will be 0. In other words, the signal is expanded in time domain. That means expansion in time domain leads to compression in the frequency domain. We can also interpret in this way. The nature of this Fourier transform is it is complex in nature. That means it will have both magnitude as well as the phase part. The application of this Fourier transform is it helps us to know what are all the frequencies that are available in the given signal. For example, here it is a 5 hertz signal, sinusoidal signal. We are able to get a line spectrum at 5 hertz. Here it is basically a 10 hertz signal. We are able to get the magnitude spectrum, that is a line spectra at 10 hertz. That means if we want to know what are all the frequencies that are present in the given signal, Fourier transform is a very good tool. But the drawback of this Fourier transform is it is a very good tool to analyze the stationary signal if the signal happens to be non-stationary. For example, here the signal has both low frequency component as well as high frequency component. We know very well that signal 1 and signal 2 are different, but their magnitude spectrum are alike. That means two different signals can have same spectra. That is the problem of Fourier transform. In order to overcome this drawback, people develop a very powerful transform called as short time Fourier transform, which is also known as windowed Fourier transform. So this is the expression for the windowed Fourier transform, W of t minus tau. So this represents the window. So we are sliding the window over the signal. We are extracting a portion of the signal and then we are taking Fourier transform for that portion of the signal. That is the meaning of short time Fourier transform. So the resolution, it depends on the size of the window. A shorter window will give very good time resolution, whereas a wider window will give very good frequency resolution. Now, this slide shows the comparison of Fourier transform with respect to short time Fourier transform. Here we have signal 1 and signal 2. Signal 1, we have low frequency component first, high frequency component next. On the other hand, in signal 2, high frequency component comes first, low frequency component comes next. If we take the magnitude spectrum, absolutely there is no difference between these two magnitude spectrum. On the other hand, if we take the short time Fourier transform, that is spectrogram of signal 1, here you can observe that the low frequency comes first, high frequency comes next. In the spectrogram of signal 2, high frequency comes first, low frequency comes next, because this short time Fourier transform has the ability to provide both time as well as frequency information. So if we want to analyze non-stationary signal, then short time Fourier transform will be a better option than Fourier transform. The size of the window decides the resolution. As we have mentioned earlier, shorter window gives very good time resolution, wider window gives very good frequency resolution. Is it possible to get both good time and frequency resolution? The answer to this question was given by Heisenberg uncertainty principle. So definitely very difficult to get both time as well as good frequency resolution. The effect of window length, it is illustrated by a very simple experiment. Here we have taken two different kinds of signal. Here it is an impulse. Signal 1, that is an impulse at the sample n equal to 5, whereas signal 2 is a sinusoidal signal. If I want to analyze signal 1, then we want to know where the spike has occurred. That means we are in need of time information. That means we have to choose a window of shorter length. So if we use window length of 2, we are able to capture where the signal has changed its magnitude. On the other hand, if I want to know what is the frequency that is available in signal 2, naturally the window length has to be increased. So if we increase the length of the window, we are able to say what is the frequency. That is, the frequency of the signal is 10 hertz. That information we are able to achieve if we increase the length of the window. That means shorter window gives very good time resolution, whereas wider window gives very good frequency resolution. The drawback of STFT is it is not able to provide multi-resolution analysis. That is the main drawback of this short time Fourier transform. Now we will try to compare Fourier transform with respect to short time Fourier transform. One is with respect to decomposition. Here in Fourier transform we are able to get frequency resolution, whereas in short time Fourier transform we are able to get both time and frequency information. The basis function is complex exponential. Here it is basically a restricted wave. The information what we are able to get here is frequency in Fourier transform. In short time Fourier transform, both time and frequency information. Fourier transform is suitable for the analysis of stationary signal, where a short-time Fourier transform can analyze stationary as well as non-stationary signal. The next topic what we want to highlight is a digital filter. Filter is basically an operation on the signal. It can be considered as an algorithm which is implemented by means of a hardware or a software. So, what is the role of the filter? One role is to confine the signal to a prescribed frequency band, or to decompose the signal into different subband, or we want to modify the frequency spectrum of the signal. For all these things, we are in need of a filter. First, let us consider the example of confining the signal to a prescribed frequency band. Here, the input signal is having low frequency as well as high frequency part. If we pass the signal through a low pass filter, we are confining the signal to a prescribed frequency range. So, this we call it as filtering action. The other action is decomposition. That means we want to split the signal into low and high frequency range, so that we will be able to capture the signal in the low frequency and the variation in the high frequency. This is a classic example. We have a square wave. If we pass it through a low pass filter, we will be able to get the approximation. If we pass it through a high pass filter, we will be able to get what are all the changes. That means high pass filter act like a change detector. So this idea, it will be clear in this slide. So here we have a sinusoidal signal which is corrupted by an impulse noise. So we can see that there are periodical impulses in the sinusoidal signal. If we pass such a signal, that is sinusoidal signal with spike, through a low pass filter, this will be the output. On the other hand, if the same signal is passed through a high pass filter, we will be knowing exactly where the spike is occurring. That means high pass filter act as the change detector. Now, how we can classify filters into different categories? So we can classify based upon whether it can handle analog or digital signal as analog or digital filter, then nonlinear or a linear filter, adaptive, optimal filter. Classic example of analog filter, it could be a passive filter or it could be an active filter. In the other hand, digital filter can be a non-recursive or FIR filter, and a recursive or IAR filter. Passive filter example is given here. Active filter, along with passive component, you have an active component here. Example of a non-recursive, that means current output will not depend on previous output, that we call it as non-recursive. Then we have recursive equation. Now first let us discuss FIR filter, then we will go to the IAR filter. Difference equation of a FIR filter is given here. So this equation, we are able to observe that current output is a function of current input and previous output, previous input. It is not a function of the previous output. That means it is non-recursive. Here M, if we choose M denotes the order. Zeroth order filter will have one coefficient as B naught. First order filter will have two coefficients. Second order filter will have three coefficients. So order and number of coefficients are related to each other. If M represents the order and N represents the number of coefficients, N will be always equal to M plus 1. If we give equal weightage to all the coefficient, then it becomes a moving average filter. That means moving average filter is a special case of the FIR filter. So moving average filter, we are going to take as the classic example. Here we are giving equal weightage to the coefficient xn, coefficient of xn minus 1, and the coefficient of xn minus 2. Then this is the equation for the 5-point moving average filter. What is the application of this moving average filter? We will try to illustrate through a simple example. Here X represents the input signal. So purposefully we have taken the signal like this. Here we can see that 9 and 6 are less than 10, but suddenly the signal is taking a high value. So 1 or 2, definitely it is a higher value when compared to the surrounding signal value, which is less than 10. So if I pass the signal through a 3-point moving average filter, what will be the output? That is what we want to analyze. So we have taken a 3-point averaging filter like this. So here the filter is symmetric. So 1 by 3, 1 by 3 and 1 by 3. So here the three values will be multiplied and then this 9 value gets modified as 5. Next, the coefficient 1 by 3 is moving like this and then corresponding multiplication and addition are happening. This we used to call it as convolution. So convolution involves multiplication, addition and shift. So this example illustrates the convolution operation. Here this 6 gets modified to 39. Now shifting operation takes place, corresponding multiplication and addition, so that the value 102 gets modified to 37. Again the process repeats so that we are able to get the other values of the signal. So x represents the input signal and y represents the output signal after passing the signal x of n through a 3-point moving average filter. Now if we observe the output, you can see that 102 is an arbitrarily high value, that is approximately we have made it equal to the neighboring value. So if we want to suppress any change in the signal, it is better to pass that signal through a moving average filter. So basically it acts like a low pass filter. How to extend that one-dimensional filter to a two-dimensional filter, it is given in this slide. So it is classically a two-dimensional moving average filter where all the pixels we will be multiplying it by the same factor of 1 by 9. So it is purely a low pass filter. Comparison of 3-point, 5-point and then 7-point moving average filter for the signal that is a sinusoidal signal that is corrupted by a impulse noise is shown here. If we increase the order of the filter from 3-point to 7-point, then the impact of noise gets reduced, but at the same time we have to observe that noise is not completely eliminated. So if we want to eliminate the impact of an impulse noise, we have to go for a nonlinear filter. In that case, salt and pepper noise, it is the equivalent to that in image is basically a salt and pepper noise. So if we want to eliminate or minimize the impact of sudden change in the signal, we have to go for a nonlinear filter, which is a median filter. Now this FIR filter, a special case of FIR filter, we have taken it as the moving average filter. So it is a non-recursive filter. The coefficients are symmetric. The main advantage is it exhibits linear phase characteristics. Because of that, there is no phase distortion. Since all the poles of this filter occur at the origin, it is inherently a stable filter. The condition for linear phase is either symmetric or antisymmetric condition. So here we are representing the symmetric condition like this, antisymmetric condition like this. Based upon this symmetric and antisymmetric condition and the number of coefficient, this FIR filter can be classified into 4 categories as type 1, type 2, type 3 and then type 4 FIR filter, which is illustrated here. So even symmetric with n being odd, we will be able to get type 1 FIR filter. Even symmetric with n being even, we call it as type 2. Then odd symmetric with n being odd, we have type 3 FIR filter. And odd symmetric with n being even, we will be able to get type 4 FIR filter. So 3 prominent ways by which FIR filters can be designed. One is window based, another one is frequency sampling, the third one is the optimal filter. The other way, non-recursive way to compute the digital filter is an IAR filter. So always it starts with the filter specification. Filter specification means gain in passband, gain in stop band, passband cutoff frequency, and then stop band cutoff frequency. Once the filter specification is known, naturally we will be designing a normalized analog low pass filter, which is termed as the prototype filter. So prototype filter, we can build that filter based on either Butterworth polynomial, we call it as Butterworth filter, Chebyshev polynomial, we have Chebyshev filter, inverse Chebyshev filter, and then elliptic filter. From the normalized analog filter, we can get the desired filter through frequency transformation. And from the desired analog filter to the digital filter, we have to go for mapping technique. That technique can be either impulse invariant technique or bilinear transformation technique, matched result transform technique, and so on. That means this is the design flow of the IAR filter. Now comes the comparison between this FIR and IAR filter. So before going for the comparison, how we can build the IR filter using Butterworth, Chebyshev, and then inverse Chebyshev filter. We know Butterworth filter is a maximally flat filter with no ripples in the passband and stopband. Chebyshev filter exhibits ripple in the passband, and inverse Chebyshev filter exhibits ripple in the stopband, and elliptic filter exhibits ripple in both the passband and the stopband. At the same time, the filter order, it will be minimum in the case of elliptic and maximum in the case of the Butterworth filter. Now comes the comparison of the FIR with respect to IAR filter. So based on number of coefficients, not coefficient, the nature of the coefficient, in the case of FIR filter it is symmetric, whereas in the case of IAR it need not be symmetric. FIR filter always exhibits linear phase characteristics. It is not like that in the case of a IAR filter. Then FIR filters are inherently stable, whereas stability is not guaranteed in IAR filter. The group delay is constant in FIR filter. It is not so in IAR filter. The order required to meet the given filter specification, it is more in the case of FIR filter, it is less. This is the attractive feature of the IAR filter. But at the same time, limit cycle oscillation, FIR filter exhibit, whereas there is no limit cycle oscillation in FIR filter. Because of this huge advantage of this FIR filter, this filter is preferred in adaptive filter. That means filter with self-tuning characteristics, we call it as the adaptive filter. The coefficient, we have to have some mechanism to vary the coefficient with respect to the external environment. So this adaptive filter are mostly non-linear and time varying filter. The general structure of the adaptive filter is illustrated here. This is the adaptive filter. The input to the filter is given like that, and the output is denoted as y of n. It is compared with the desired response. The difference between the desired response and the output, we call it as the error signal. The error signal along with the input will be passed through an adaptive algorithm. The adaptive algorithm, two prominent algorithms are LMS algorithm, RLS algorithm. The main idea behind this algorithm is new weight is equal to old weight plus correction term. That means it is an iterative algorithm. Every time we are changing the weight till we achieve the convergence. That is the idea behind the adaptive filter. For what applications we are going for adaptive filter? One of the prominent application is system identification. Then we have inverse system modeling, noise cancellation, prediction. So system identification, here the adaptive filter is connected in parallel to the system under study. That means here adaptive filter is connected parallel. Once the system achieves convergence, then the adaptive filter will mimic the unknown system. This we call it as the system identification. The next application is inverse system modeling. Here the adaptive filter will be connected in cascade to the system. The error is given like this. The error will be again fed to the adaptive filter. Now this system is used for channel equalization. So we have different applications of the adaptive filter. Then for what are all the domains we can apply this DSP algorithm? So applications of DSP with respect to electrical engineering, what are all the various application? Electronics and communication engineering, biomedical engineering, instrumentation and control engineering, civil engineering, and mechanical engineering. We want to give an overall view or bird's eye view of different applications of DSP algorithm in different domains. So in electrical engineering, power line signal analysis, fault detection in motors. In consumer electronics, and then in multimedia with respect to ECE domain, biomedical signal analysis as well as image analysis in biomedical engineering domain. In INCE, with respect to data fusion, multi-sensor data fusion and system identification, DSP algorithm plays a important role. In civil engineering, structural health monitoring, seismic signal analysis, and in mechanical engineering, how to analyze the vibration. What are all the tools that we can use to analyze vibration? Whether we can use Fourier transform, short time Fourier transform, wavelet transform, and so on. So these are all the broad applications of DSP. And this slide explains on what basis we have written this digital signal processing book. So the ultimate objective of writing one more book on DSP is like this. Here, this idea of writing the textbook emerged from one concept. That means how to write a comprehensive text which covers both the fundamental concept as well as the advanced concept of signal processing. Whenever we talk about DSP, as I've already mentioned, three important topic which is related to DSP are generation of signal, analysis of signal, and processing of signal. During generation, we have sampling and quantization concept. During analysis, we have transform. The transforms which are discussed in this particular text include Z transform, Fourier transform, and then short time Fourier transform followed by wavelet transform. With respect to system, mostly we have covered linear filters, how to design linear filter using pole zero technique, FIR filter, and then IAR filter. How to realize the filter using direct form one structure, two structure, cascade, parallel, and then lattice ladder. All these things are covered in structure of the filter. And what are all the issues that will come whenever we want to implement the algorithm, that is discussed in the chapter of finite wavelength effect, and how to choose a hardware in order to implement the digital signal processing, whether we have to go for a fixed point processor or floating point processor. All these issues are addressed in chapter number 17, which is digital signal processor. Then how to move from deterministic signal processing to stochastic signal processing. So as long as the signals are deterministic, there is no issue. Once the signals are stochastic, naturally we have to go for some other technique. That technique we call it as the power spectral density. So in power spectral density, we have addressed parametric method, non-parametric method, and the subspace method, and how to move from single rate system to multi-rate system. So the concepts like downsampling, upsampling, noble identity, filter banks, transmultiplexer, all are discussed in multi-rate, which is covered in chapter number 14. Then idea of adaptive filters, LMS algorithm and its variant along with RLS algorithm, it is given in chapter 16. And what is the use of studying all this algorithm, how it is applied to real world. So that is given in chapter number 18. Overall applications of DSP in different domains of engineering, it is addressed in chapter number 18. That means this book comprises of 18 chapters, and each chapter we have the following, the significant features of the textbook we want to summarize like this. This book covers both the fundamental as well as the advanced topic. That means comprehensive coverage of DSP as well as ADSP topic. That means it is useful for both undergraduate as well as postgraduate students who are interested in learning signal processing algorithm. Lot of numerical examples are discussed in this particular textbook. So this will enhance the analytical skill of the student. MATLAB demonstrations, wherever possible, we have given the MATLAB demonstration that will help to understand the concept in a better way. Multiple choice are given at the end of each chapters. It will help the students to prepare for competitive examinations like GATE and other examination. Each chapter we have given lab experiments. So this textbook can be used for both theory as well as the lab course. For the instruction, a solution manual is provided which covers the solution to all the exercise problems. So based upon request from the instructor, it will be given to the instructor through McGraw Hill. So we have prepared an exhaustive solution manual. So the instructor can get the solution manual upon request to the McGraw Hill representatives. These are all the references, and if there are any questions, we are glad to receive the questions from the audience. Kindly feel free to write your questions or post your questions so that we will be glad to answer those questions. Shall we ask the audience to post the question in the chat box, sir? So, which filter do you recommend for fault signal containing DC component and transients? So, DC offset will also be there. Definitely, I agree with Amrita Sinha. So, filter, for example, uh, if you consider different types of faults, so it can be a transient as well as DC offset. In general, if you want to detect any change in the signal, you have to go for a high pass filter. If you want to decompose the signal into different frequency component, better to go for wavelet transform. Wavelet transform has the ability to decompose the signal into low and high frequency region. In that case, wavelet decomposition will be a better choice. The question 2, how fault type can be detected. So different types of faults in power line that I have shown. One is we have spike, next we have sag, then we have swell, then we have offset problem, harmonics. So how you can detect this fault? So it's a good question. Actually, we can detect the fault through signal decomposition. So lot of techniques are available for signal decomposition. Either we can go for wavelet decomposition, or we can go for empirical mode decomposition, or we can go for variational mode decomposition. So signal decomposition is the way by which we can detect different types of faults. What is the physical application to perform transform in our lives? So it's an interesting question. So let me take the question in this way. What is the use of taking transform? I hope the audience, they want to know the impact of the transform. Transform helps us to visualize the signal in a different way, that's all, without affecting the signal. So ultimate objective is to extract the information from the signal. That is the reason for going for transform. Transform gives a different view of the same signal. This is what I can put it in a simple sentence. So that is the question from Krishna Singh. That is the role of transform in our life. Any other questions, sir? So one more interesting question from the audience, Mr. Jitendra Singh. Can we mix two signal? First one contains information and the second contains access permission, and the system allows only resisted consumers. Restricted consumers, or is it resisted consumers? I don't know. Here, I think he is talking about one is modulation, the other one is security. So security, naturally, either we have to go for a cryptography or steganography algorithm. Definitely it can be done. So we can mix two signals. So whenever you talk about mixing, it is some kind of a modulation. At the same time, I want to ensure the security of my information. Naturally, it can be done by means of either steganography approach or watermarking approach, cryptography approach. So definitely it can be done. So it's an interesting question from Mr. Arvind Murugan. Which filter is best? So it's $1 million question, I could say. The reason is you can consider your disease similar to that of noise. Noise is similar to that of disease. Your filter is similar to that of medicine. That means you cannot have one medicine which can cure all the diseases. That means you are in need of different medicines for different diseases. That means your noises are similar to that of diseases and your filters are similar to that of medicines. That means there is no universal medicine which could solve all the diseases. That means there is no one filter which can solve all the problems, which can minimize all the noises. That is the reason why there are different types of filters that are existing. Each filter is unique in its own way. Some way, in some time, your nonlinear filter performs better than a linear filter. In some scenario, your linear filter may perform better than a nonlinear filter. In some situation, it is absolutely necessary to go for a optimal filter. In some situation, you have to go for a adaptive filter. So a very interesting question. Thank you for asking a question. That is, which filter is best? In my words, it's a very difficult question. There is no filter as this is the best filter to solve all kind of noises that are occurring in the signal, or to tackle different types of noises in the signal. That is, noises are like diseases and your filters are like medicines. Have I answered your question, sir? Okay, one more interesting question from Mr. Om Prakash. That is difference between DFT and FFT. Actually, FFT is computationally efficient form of DFT. It is not a new transform. It is an algorithm which can implement DFT in a better way. That's all. So FFT is not a new transform. I want to emphasize this point here. Fast Fourier transform is not a new transform. It is computationally efficient form of DFT. That FFT, people are developing it in different strategy. It can be radix 2, radix 4, split radix, decimation in time algorithm, decimation in frequency algorithm. But whatever may be, it is only computationally efficient form of DFT. It is not a transform by itself. I hope I have answered Mr. Om Prakash question. Any concept like spectrum image, shall we take spectrum image instead of spectrogram? Again, an interesting question from Mr. Arun P. So first we have to understand what do you mean by spectrum image. We know very well that spectrum means we are able to know what are all the frequencies that are available in the given signal. So here we have magnitude spectrum as well as phase spectrum. If we go for Fourier transform, we know very well that image has got frequency, that is variation in intensity along x and y direction. We call it as the frequency of the image. Here, shall we take spectrum image instead of spectrogram? So here spectrogram refers to square magnitude of short time Fourier transform. So that is what spectrogram implies. It means we are taking the square magnitude of the short time Fourier transform. So the question is little bit ambiguous. So can you pose the question so that we can understand the meaning of the question correctly? These are two different. Spectrum means taking the magnitude spectrum of a signal, which can be either a one-dimensional signal or it can be a two-dimensional signal. Spectrogram means we are taking square magnitude of the short time Fourier transform. It can be applied to both one dimensional as well as multi-dimensional. So if you take spectrogram of a one-dimensional signal, you will be able to get two-dimensional information. This is what we have to be little bit careful. So if we take a one-dimensional signal, if we take spectrogram, we will be able to get a two-dimensional representation of a one-dimensional signal. I hope I have answered his question. Any other questions? So few more question is, can you share the PPT of this session? This is another question. Surely you can contact McGraw Hill person. So definitely they will be ready to share this video through YouTube, as well as based upon request they will be able to share the content. So Mr. Arun P has again raised, is there any concept like spectrum image? Definitely, image is a two-dimensional signal. It has variation along x and y direction. Whenever there is a variation along x and y direction, we can take the spectrum. Definitely, we can take the spectrum of the image to capture the variation along x and y direction. Thank you very much, Mr. P. Arun. So one more question from Mr. Armuga Babu. Can you mention the applications of IAR filter? So definitely it is an interesting question. Nowadays, if we want to realize a filter with minimum number of coefficient, there is an option to go for IAR filter. But we have to be little bit careful that we cannot expect linear phase characteristics, and we have to be very cautious that it should not be a unstable system. So stability is not guaranteed, as well as linear phase characteristics. So much of the time has to be spent to ensure that the filter is exhibiting linear phase and is stable. That is the reason why people are little bit hesitant to use that IR filter, but it has got a strong theoretical background. So all your IR filter comes from analog filter theory. Can we get the book specimen copy as well as the solution manual so we can refer to students? This is the question by Devendra Pratap, Mr. Devendra Pratap. Sure, sir. We will be able to share the e-copy as well as the hard copy to you based upon request. So you can request the sales representatives of McGraw Hill. Definitely they will be able to share the e-copy as well as the hard copy. And one more question from Dr. L. Sivagami. What is the practical use of convolution? Again, it is an interesting question. Two important mathematical operations in DSP are convolution and correlation. Convolution, the practical use is convolution basically performs filtering operation. Even though correlation operation is mathematically similar to convolution, the application of correlation is template matching. So if we want to find the relative similarity between two signals, we have to go for correlation. If we want to filter, naturally we have to go for a convolution operation. So immediately what I can say is practical use of convolution is to perform filtering. Again, when you do filtering, there are two choices. Either we have to go for a low pass or a high pass. Low pass filter performs approximation, whereas high pass filter is allowing us to get the details or change detection. I hope I have answered to that question. What is a normalized filter? The cutoff frequency is 1 radians per second, sir. That we call it as the normalized low pass filter. That is the question put forward by Mr. Ravi Kumar M. Again, there are many requests for sharing the slides. Definitely we will go for it. So most of them are asking for specimen copy. Surely we will be able to share the specimen copy to the instructor. So we also want to get the feedback from you. So we have written the book. Now it is open. You can access the book. You can go through the book. You can analyze the content. Whatever feedback you have, feel free to share it with us. Definitely it will be helpful for us to analyze the content in a better way. So you are the readers are the ultimate judges. Based upon your view, naturally we can incorporate the changes in the subsequent edition. Thank you very much for patiently attending to this webinar. Now I want to thank the McGraw Hill for giving me the opportunity to interact with you all. Next, I want to thank my co-authors, Dr. T. Veerakumar and Dr. Badri Subudhi, because of their constant encouragement and motivation, we could do this. Now, I wish to thank all the participants who patiently listened to this lecture and you have raised lot of questions. Definitely, it helped us to view signal processing in a different way. One more question: which language, software, and hardware best for DSP? Again, it's an interesting question. Either we have to go for a proprietary software or a open software. So if we want to use proprietary software, MATLAB definitely it is a good source. If we want to go for open source, then we have to go for either Scilab or Python. So Scilab, Python, Octave, definitely they are better choices if we want to implement algorithm in a open source platform. If we want to implement DSP algorithm in a proprietary way, we can go for MATLAB, LabVIEW, and so many proprietary softwares are there. So I wish to thank all the participants once again for raising interesting questions. So feel free to write to us. Definitely your feedback will help us to improve the content in a better way. Once again, thank you very much. Thank you, one and all.